Hello everyone and welcome to lecture 37. So until our previous class we have looked at the cost minimization problem. So we have divided it into the long run and the short run, and if you recall, in the last couple of lectures we have introduced the notion of long run cost minimization. Recall, in the long run both labor and capital are decision variables for the firm. So I am choosing the amount of labor and the amount of capital. If you prefer, we are finding the input demands given a specific price for labor, which is given by the wage rate, and a price for capital, which is given by the rental rate of capital. To be precise, we looked at a specific example wherein we said, suppose the production function is Q is equal to 10 times square root of L times K. Then we were given the per unit price of labor and the per unit price of capital, and we said what is the minimum cost function, right? So generally we don't use the word minimum, because the cost function, whenever we use the word cost function, we essentially mean that it is the lowest cost incurred by the firm to produce a given level of output at the input prices W and R. So given this production function, we said that there are two conditions that I need to write. The first is that my optimal amount of labor and the optimal amount of capital must be on the isoquant. So it must satisfy the functional form Q is equals to 10 times square root of Lk. The second condition that we wrote was the tangency condition, wherein we said that at the cost minimizing bundle, the iso cost line is tangential to the isoquant at that point B, which is to say that the absolute value of the slope of the isoquant is equal to the absolute value of the slope of the isocost line. Mathematically, it means MPL by MPK equals W by R. So we are solving for the two unknowns L and K, and these are the two conditions that we use. Now, to produce a generic Q level of output, we did this example and we found that the optimized L as a function of output is Q divided by 5. And the optimized K as a function of output is Q divided by 20. Therefore, the long run cost function took a linear shape, which is 8 times Q. And in the last class, I had asked you to check, does the production function exhibit increasing, decreasing or constant returns to scale. I hope you have been able to solve that example. Then we said, well, what happens if the input price of labor changes? So suppose the wage rate becomes higher. So previously it was 20 rupees per unit, now suppose it becomes 30 rupees per unit. So we can again repeat this exercise. We will again get a new long run cost function because the input prices have changed, specifically the price of labor has changed. And in this graph, pictorially we were able to show that if the input price of labor changes and we still want the firm to produce 140 units of output, it is going to be more expensive for the firm because the C hat, which is the cost associated with this isocost line passing through the point D, is greater, the rupee value is going to be greater than C bar, which is equal to rupees 1120, right. Where did we get that 1120? Recall, the long run cost function at input prices 20 and 80 is given by the function 8 times Q, and we are producing 140 units of output. So 8 times 140 is 1120. Okay. Now, we have computed the input demand for labor. Now, we want to look at the short run cost minimization problem and then compare the short run problem with the long run cost minimization problem. So, short run cost minimization. So, let us first get a pictorial understanding of this and then we will take a specific example. So, on the x axis I have labor and I have capital on the y axis. Suppose the firm wants to produce Q0 amount of output, right. We are given some input price of labor, some input price of capital. So that tells me what the isocost line is. So in the long run, what will I do? I will look at the isocost line, which is going to be tangential to the isoquant at some point. Let me call this point to be point A, right. The amount of labor that I am using is L sub A, and the amount of capital that the firm is using here is K A, right. So if you tell me exactly what the value of Q0 is, if Q0 was 140, if W was 20 and R was 80, as was the case for the previous example, we would get the values of L and K based on the example that we solved. I think K was 7 and L was 28. Now, suppose for a moment that the output, the firm wants to produce more units of output. So, let us say that the output now has increased. The firm wants to produce more output. Well, why does, so let us say the good is tables. Why does the firm want to produce more tables? Perhaps the demand for tables has increased. So, the firm also wants to increase its production from Q0 to Q1. So, which means the firm is going to move to some other isoquant, so which is at a higher level. So, Q1 is greater than Q0. Now, clearly the bundle A, so the initial optimum for producing Q0 units of output was LA and KA. Clearly, that bundle is not going to be sufficient to produce Q1 quantity of output. Now, what will the firm do? The firm will again resolve its optimization problem. It will write down the two conditions, that the optimal amount of L and K must be points on this isoquant Q1. It will also write down the tangency condition, that MRTS is equal to minus W by R, which is to say that MPL by MPK equals W by R, and we will get some other cost line passing through this point, which is tangential to this isoquant at Q1. So, let us say that point is B. So, as before, we will solve the long run problem, and at the new long run problem, let us say in the long run, because now I could choose both labor and capital, in the long run, if the firm has to produce Q1 quantity of output, it will solve its cost minimization problem again, and choose the input bundle B, which is LB amount of labor and KB amount of capital. Now, from this graph we can see that the amount of labor and the amount of capital that the firm is using both has increased. Now, this could likely be because that I am producing more amount of output, so I need more amount of labor and more amount of capital. So, that tells me that I have LB amount of labor and KB amount of capital. We can also notice what the long run cost is going to be. Well, the cost in the long run, so I will put an L to indicate that I am talking about cost in the long run as a function of to produce Q1 units of output. In fact, not a function, I am specifically interested in producing Q1 units of output, is going to be W times LB plus R times KB. And since LB and KB both are larger than LA and KA, clearly CL of Q1 is going to be greater than CL of Q0, right. So, this is the long run cost. Okay. So, keep this in mind. Now, this is not anything new that I am saying, this is exactly what we have done in the previous example also, but I have now, the only thing I have changed in this example is that I have increased the output from Q0 to Q1. Now, suppose the firm was in the short run and that capital was fixed at KA, right. So, suppose I could not change capital. So, if I cannot change any input, the firm is supposed to be in the short run. So, the only input that it can change is going to be labor. So, the only decision for the firm is to choose L. So, the question is, in the short run, what is the amount of labor the firm will choose? Now, if I am fixing capital at K bar, right, I am fixing capital at K bar, it means that this is no longer my choice. So, in a sense, I could essentially draw a line here and tell you that the amount of capital that I can use is only KA. How did we get KA? KA was the cost minimizing bundle, cost minimizing amount of capital when Q0 units were being produced at input prices W and R. Now, if the capital is fixed at Ka and you want me to produce Q1 quantity of output, well, essentially this is going to be some production function, Q is equals to f of Lk, right, and you have fixed capital at K bar and you want me to produce Q1 quantity of output, then the amount of labor that I must use must be this point, right. So, recall the labor capital combinations must be points on the isoquant. So, let us call this to be LD, this is the point D, right. So, if I am already fixing capital to be K bar is equal to, let us say 5 units or 7 units, and you are insisting that I produce Q1 units of output, then I have no other choice but to figure out what the L is based on my production function. So, I can write this as L comma D, L sub D, right. So, LD comma K bar is an input combination which is going to allow me to produce Q1 units, and I obtained this by simply identifying what is the L from my isoquant. Now, what is the cost associated with this bundle D? Well, this is the cost in the short run. So, I will put an S here to produce Q1 quantity of output given that my amount of capital is equal to Ka. So, that is the notation I am going to use. So, whenever we are going to talk about cost in the short run, well, it is the cost incurred by the firm to produce a given level of output at a level of capital which is fixed, and in this case the level of capital is fixed at K bar which is equal to K. Now, this cost is going to be W times LD plus R times K bar or Ka. So, this is the same as W times LD plus R times Ka. Now, notice, compare CL of Q1 with CS of Q1 comma Ka. While the amount of labor has increased, the amount of capital has decreased. So, a direct algebraic comparison may not be very meaningful, but from the picture I can see that what if I draw an iso-cost line passing through the point D, well, that cost level is going to be CS rupees. So, this is the amount of expenditure that the firm has for buying this input bundle D, which has LD amount of labor and K bar equal to Ka amount of capital. So, if I were to plot a generic iso-cost line, that cost line would be CS of Q1 equals WL plus RK, which is to say that K equals CS of Q1 upon R minus W upon R times L, which means if I were to draw a line which is passing through the point D and is parallel to all the previous iso-cost lines, that is going to be a line in red. That line, notice, is going to be at a higher cost level compared to the blue line. Well, the blue line is my CL, right. That is the cost incurred by the firm when it could choose both labor and capital. However, the red line, in fact, I just have one point here, the point D. What we have done is, we are trying to find out the rupee value of the cost associated with the cost line passing through the point D, that is going to be CS. So, clearly CS is a higher level than CL. So, CS Q1 comma Ka is going to be greater than CL of Q1. So, the inference here is, or the main takeaway here is, that the cost in the short run is going to be greater than the cost in the long run. So, cost in the short run to produce Q1 units of output is going to be greater than the cost in the long run to produce Q1 units of output. And intuitively it is also making sense, right, because between the long run and the short run, it is the short run which is more constrained, right. So, imagine that you have a room with 2 exit doors, right. You may choose to use any of the exit doors. So, the choice that you have, right, when both the exit doors are available is the long run problem, right. I may choose to exit from the door on my left or on the door on the right. But let us say if I close the door on the left and only one door is available, right. So, that would be the short run case wherein you have taken away some amount of flexibility from me. Well, for the firm taking away the flexibility was the ability to choose capital. In this example, you have taken away the flexibility to exit the room from the door on the left. I could still exit from the door on the right, of course, but in the long run, I did have the choice of exiting from both the door on the right as well as the door on the left. So in the long run, I'm going to be more happier. So for the firm, more happiness means lesser amount of cost. So in the long run, the firm is going to incur lesser amount of cost to produce a given level of output compared to the cost that it would incur in the short run. Okay. So this is a pictorial representation. Let's take a specific example and convince ourselves. So let's first look at the same example that I had earlier. So suppose I have Q equals 10 times square root of Lk, right? This was initially the problem where we wanted to produce Q0 equals 140 units of output, and let's say the price of labor was rupees 20 per unit of labor, R is equal to rupees 80 per unit of capital, right? So sometimes I may be in a hurry not writing the units of labor and capital, but when you are reviewing this, please make it a habit of writing that the wage rate is rupees per labor R and the rental rate of capital is rupees per unit of K, right? Now we have solved this example. We learned that the cost in the long run to produce 140 units, the long run cost to produce 140 units was rupees 1120. We have already solved this example, right? And to represent this in the picture, this was, if you recall, you had the isoquant Q0 equals 140 and we had the isocost line, and we solved for the amount of labor and the amount of capital. The amount of labor was 28 and the amount of capital was 7, right? So this was the long run problem. Now suppose in the short run, the amount of capital is fixed at 5 units, right? So now you don't have a choice. The amount of capital that is available is only 5 units, okay? So where do I have the 5? It is here. So the K bar is equal to 5. So essentially now notice, if capital is fixed at 5, you have taken away the ability of the firm to choose one of its inputs, which then means that the amount of labor that I will choose must be equal to whatever this point is, right? And the black line is associated with an isocost level of 1120, rupees 1120. So this is, let's say, the point A, and now the bundle that I have is the bundle B. So let's solve for the amount of labor that the firm is going to use. Now how do I solve for it? Given that the production function is Q equals 10 times square root of Lk, you want me to produce 140 units of output. That's 10 times square root of Lk. L is the amount of labor that I am using, and K bar is fixed at 5. So this essentially means that 5L is 14 times 14, which means that the L at B is 14 square divided by 5. If you do this arithmetic, you are going to get 39.2 hours, right? So the new bundle for the firm involves a choice of labor which is equal to 39.2 labor hours, and capital is fixed, of course, at 5 units. So this is 39.2. Even on the graph, you can see that the amount of labor is to the right of 28. So what's the cost associated in the short run? So the cost associated in the short run to produce 140 units of output, given that K bar is equal to 5, is going to be the per unit cost of labor, which is 20, times the amount of labor that I am using, 39.2, plus the per unit cost of capital, which is 80, times the amount of capital that I am using, which is equal to 5. Now this arithmetic, 20 times 39.2, so that's going to be equal to 784 plus 400 is going to be equal to rupees 1184. So the the cost incurred by the firm to produce 140 units when I have 5 units of capital is 1184, which is going to be greater than the cost that the firm incurs in the long run to produce 140 units, which was 1120 rupees, right? So clearly this is a numeric, so the fact that you have put a constraint right? Now, I did not let capital equal, if the capital was equal to 7, then of course, I would have chosen the same amount of labor as 28, and in that case, my cost in the short run and the long run would have been same. We will look at that cases separately. Suppose magically I had kept the amount of capital to be exactly equal to the cost minimizing amount of capital that I had in the long run, then the cost in the short run and the long run both would have been the same. But instead, the amount of capital was fixed at a level 5, which allowed me to use 39.2 units of labor, 39.2 labor hours if you prefer, and I ended up with a higher cost. Now, if I draw the ISO cost line passing through this point B, well, what would that be? So, this is the point B is associated with the rupee value of cost, which is 1184, and all the ISO cost lines have a slope which is minus W by R, which is equal to minus 1/4 here. So, I am going to get a line which is going to be parallel to the black line. So, this line is associated with a cost of 1184. So, the cost level here is in the short run. So, the red line denotes the ISO cost line passing through the point B, and notice recall the definition of the ISO cost line. ISO is same, ISO cost means same cost. So, all bundles on the red line are associated with a cost level of 1184 rupees. All right. So, this was for a particular unit of output which is equal to 140 units. Now, suppose I want to generalize this, right. So, I want to generalize the example. As before, suppose I wanted to produce based on the production. So, my ISO quant was Q equals 10 times square root of LK, right. So, the price of labor was W equals 20, input price of capital was R equal to 80. We have solved the example of the long run cost function. If you recall, the long run cost function was CL as a function of Q was 8 times Q, right. We have solved this example before, right. So, if you notice, the long run cost function, we have derived it was 8 times Q. So, this is the long run cost function, right, wherein I could choose both the amount of labor and the amount of capital. Now, I want to repeat this exercise for the short run, right. So, I want to find the short run cost function. So, the short run cost function when K bar is equal to 5 units, K bar is equal to 5 units, right. Now, if K bar is equal to 5 units, what will I have? So, essentially now I am going to have Q equals 10 times. So, from the production function, because notice once you fix the amount of capital to be 5 and you want me to produce Q units of output. So, Q is equal to 10 times square root of L times K bar, which is equal to 5, is what is going to determine the amount of L. You tell me Q is 140, I will tell you that L is equal to 39.2. You tell L that Q is equal to 200, I will again use this production function to solve for what the L is. So, squaring both sides, I will get Q square equals 100 times 5 times L, which is 500 L, which means that L as a function of Q, I will put an S to denote that I am talking about the short run case, because capital is fixed at 5, is going to be Q square by 500, right. So, this is the functional form of L. So, now you tell me what the Q is, I will plug in the Q there and tell you what the exact numerical value of L is. So, once I have this functional form, what is the short run cost function at K bar equals to 5? Well, it is the wage rate times L, which is Q square by 500 plus R, which is 80 times K, which is equal to 5. So, this gives me, so we can cancel the 0 and the 2 and 50 is going to give me a 25. So, that is Q square by 25 plus 400. So, my short run cost function takes the form 400 plus Q square by 25. What was the long run cost function? The long run cost function was 8 times Q. So, the long run cost function was linear. However, the short run cost function is non-linear. if I want to plot the short run cost function, what will that look like? So, cost functions are always plotted in the output and rupee space. So, on the x axis I have output and on the y axis I have rupees. So, if q is equal to 0, the cost is going to be 400. In fact, this could be treated as a fixed cost, right. So, no matter what, in fact, it is the fixed cost, right, because I am stuck with 5 units of capital whether I produce or not. Each unit of capital is going to cost me 80 rupees. So, 5 units of capital will cost me 400 rupees. Okay. So, this is the fixed cost. There is also a component which is q square upon 25, which is nonlinear in q, and as q increases, this component increases. So, my cost function is going to take this particular shape. So, this is the CSQ k bar equal to 5. Right. So, given the various values of q, I can plug those values of q and identify what the particular rupee value of the cost is. Right. So, to summarize, what have we shown so far? We have solved the cost minimization problem in the long run. We have identified the L star and the K star that the firm chooses in the long run. Using that, we have identified the long run cost function. That long run cost function is a function of the output. Then we have repeated the exercise in the short run where the amount of capital was fixed. So, capital was fixed at k bar is equal to 5, and then we used the isoquant to determine the amount of labor. Once I had that, we used WL plus RK to figure out what the short run cost function was. And in this case, the short run cost function is non-linear, which is q square upon 25 plus 400. And we have said that the cost in the short run is generally greater than the cost in the long run, which leaves us with a question: can the short run cost and the long run cost be equal? Okay. Now, we will answer this question. The short answer to this question is yes, they can be equal under certain specific conditions. But before we do that, I need to tell you how to draw cost curves. Now, we will get to cost curves, but to sort of close this entire discussion, I want to also talk about what can we say about the input demand in the short run. Recall in this example where we had changed the wage from 20 to 30, the amount of labor actually decreased, right. So, that gave me the labor demand curve based on the price of labor versus the quantity demanded of labor, because these are inputs that the firm is using. This I did in the long run. Here capital was actually variable. We solved the cost minimization problem under two cases. One, when the input prices were 20 and 80, price of labor was 20, price of capital was 80, and then we solved it again when the price of labor was 30 and the price of capital continued to be 80, and it gave us this particular downward sloping line. What we want to do is we want to solve a similar such case and ask what can we say about the input labor demand curve, right. So, one of the inputs, because capital is fixed, labor demand curve in the short run, right. So, we want to take a particular example. We want to study this in the context of a very interesting example wherein we are going to have some fixed amount of capital, and we are going to see that if capital is fixed at that particular level, which means I am in the short run and I am given various wage rates, if the price of labor were to change, how does the optimal amount of labor that the firm is going to choose going to change? So, we will do that in our next lecture. Thank you.